Okay. Uh, the first problem is not too bad. You've seen this, even though you may not have heard this terminology before. The direct product, you actually sort of do it in linear algebra when you have like R and R2 and R3. When you have higher dimensional vector spaces, this is sort of what's going on here, or it's a special case of this. If I have two groups, G and H, I can sort of take those two groups and stick them together as coordinates and make a bigger group called the direct product, where the multiplication of the ordered pair is just do what's appropriate for G in the first coordinate, do what's appropriate for H in the second coordinate. So it's a way to build, if you've got two groups, you can build a bigger one. If you got one group, you can just take the direct product of that with itself, for example. That's how you build R squared out of R and so forth. So prove this is a group. That shouldn't be too difficult. Show if I have subgroups G prime of G and H prime of H, then G prime cross H prime is a subgroup of G cross H. And I've got a follow-up in number C, is every subgroup of G cross H of this form. So you can build subgroups of this form of the direct product, but is any subgroup of that form. Prove this is true or give a counterexample. And finally, show that the direct product of G and H is abelian if and only if both pieces are abelian. To do two, there's going to be a theorem I will either get to late today or on Monday that will be very important in this, and that is if you have a group of order p to the n, it's got a non-trivial center. That'll be important in this. But what I want you to do here is if you have a finite p group of order p to the n, so it's just some group of order p to the n power, finite, then for every k between 0 and n, there's a subgroup of order p to the k. So it's got, if it's got p to the n, it's got a subgroup of order p to the n minus 1, p to the n minus 2, all the way down. And each subgroup of order p to the k is normal in the subgroup of order p to the k plus 1. This is important for some stuff that we've got coming up as well. Finally, number 3 is a generalization of number 1. This is called not the direct product, but the semi-direct product. And it looks like somebody came up with this on some April the 20th. It's crazy because what you have is you have this homomorphism from H into aught G. And we define the semi-direct product with the multiplication. The direct product, you just do what you do in these two coordinates. This has a little twist on it because when you multiply these two things, H1, H2 is just the way it was up here, but this has a twist on it. So this is G1 phi of H1 G2. Now remember, phi of H1 is an automorphism of G, so this does a little twist to G2. It does this. Show that this definition is a group. Show it's all the stuff. It's associative. It's a pain in the butt, and I apologize, but it's doable. You can show it's associative. It's got an identity, inverses, all that business. And for appropriate groups G and H and a homomorphism, so you have to find these. Write the dihedral group Dn as the semi-direct product of two groups G and A. Okay, any questions on that? Questions? Okay. So this is what we were working on last time, this business with the relation. So you have a group G and it acts on some set A. Then I declare the two elements are related if A is related to B, if B is can be realized as G acting on A for some G and G. This forms an equivalence relation. And we proved last time that this, in fact, indeed was an equivalence relation. And what's left to us is this last bit. This is the orbit stabilizer theorem. So what we want to do is I want to show that the size of any equivalence, so pick an A in the set, show that the size of the equivalence class of A, which by what we did before, that's the orbit of A, the length of the orbit is the index of the stabilizer. So if you look at everywhere that A goes, so you take A and you multiply by, or you act on by everything in G, that makes its orbit. How many different things there are in here is the index of the stabilizer. So let's see why this is true. So proof continued. The equivalence class of A, well, what is this really? This is the set of X in A such that X is related to A, which is the set of X in A such that G for some G and G, which is precisely orbit of A, right? Because this is the definition of the orbit of A. So I want to figure out what's the size of this thing, right? And I'm even going to do this in the case that this is an infinite set. So I'm going to do something a little bit more general. So let's let L set of left cosets of GA in G. So of course, GA is some subgroup. It's just stabilizer of A. It doesn't matter whether it's normal or not. It's got some collection of left cosets. So that I'm going to let L be my list of left cosets. And I'm going to define a function from L into the equivalence class of A, and well, anybody want to guess how I might want to do this? I'm going to do F. So if this is a left coset, my input should be so the left coset looks something like this. It's just some left coset. And I want this to barf out something that's in the orbit of A. Any guesses what I might try? Well, to get something in the orbit of A, I've got to act on it by something in G, right? Why not this one? Let's just try that. Right. Now, what's the first thing that I have to worry about here? Is this or is this not well defined? Because there may be different ways to represent. I mean, I just happen to write this G, capital G of A down. There might be different coset representatives. So we need to show that this is a well-defined function. So to that end, let X G of A sub A equal Y. So suppose that we have two different, possibly different representatives of the same equivalence class. What does this mean? These two cosets to be the same. This means that Y inverse X is what? It's in G sub A. Right? That's what it means for these two cosets. These two cosets represent these two cosets are the same if and only if Y inverse X is in GA. Right? Yes. Sorry, never mind. So what does this mean? This is what it means for Y inverse X to live in GA. It means when you act on A, it leaves it alone. Right? And this is Y inverse acting on X acting on A is A. Now hit this on this side with Y. And so Y inverse cancels, and I get X acting on A is Y acting on A. So F of XGA equals f of YGA. And f is well defined. Because if you use the X rule and I use the Y rule, we get the same answer, right? So, okay, we're good to go. This function is well defined. Okay. Now, my next move is I want to show that this function is not just well defined, but it's a bijection. So we know that f is a function. F is 1-to-1. Let's show that. Suppose f of xga equals f of YGA. Well, this means X acting on A is Y acting on A. Everybody agree with that? Now I'm gonna act my Y inverse on both sides of this on the left. And this gives me, if I simplify this a bit, Y inverse X acting on A is A. Agree? So what does that tell me about Y inverse X? Where does it live? Well, a little bit more general than that. Yeah, it has to be G of A, because what Y inverse X did is it stabilized A. It left A alone. So Y inverse X actually lives in GA. And what does this mean? If Y inverse X is in GA, that means the left coset YGA is equal to the left coset XGA. And so F is 1-to-1. Because F of Bill equals F of Fred means Bill equals Fred. Everybody okay with that? Yes.
So here GA is the stabilizer.
Yeah, that's right.
Could you do a brief review of what that means?
Oh, sure. I mean, G of A is just this. This is the set of, say, Z in G, such that Z acting on A is A. It's just a collection of everything that leaves A alone. And that's where the subscript A comes from, that it leaves that particular A alone. Okay so far? Okay, the last thing I guess we need is onto. So let's see if we can do that. So how about onto? So onto. Suppose V is in orbit of A. Right? What does this mean? Then B is equal to G for some G and G. Therefore, B F. So F. What do we have? We have the map F from L into orbit of A, or the equivalence class A, whatever you like, is a bijection. And if you remember from 3190, when you have a bijection of two sets, that means that they're the same size. So the cardinality of L is equal to the length of the orbit. But the number of left cosets is the index. And there you have it. Okay. Any questions on this? Okay, so we've talked about this permutation representation, right? Where what it is it's a homomorphism from G into the permutations, permutations of G if it acts on itself. Let me give you a concrete example of how permutation representations. Here's a good example. So let's just take a simple example. Let's look at Z6. I'm going to give you what I hope is sort of a concrete look at some examples of permutations, how you might think about permutation. Let's let G act on itself. So here, my set that I'm acting on is G itself. I usually call this left multiplication. I'm going to call this left translation. Because I'm not really multiplying. The group operation here is addition. So here's the way what I do. G acting on A is G plus A. Here, of course, the identity is 0. When 0 acts on A, it adds 0 to A. It doesn't change anything. It's easy to see that this is actually a group action. So if I were to think of a permutation representation induced by this operation, let's see what 0 does. Z6 by stabilizing everything. So I would think of this as the identity permutation. That right there is very instructive, right? I mean, so 0 adds to any of those things, it leaves it alone. 1 does something interesting. What happens with 1? Let's see what happens. What happens when I add 1 to 0 bar? What do I get? Right, so actually, let me do it this way. So 1 plus 0 bar equals 1 bar. 1 bar plus 1 bar is 2 bar. 1 bar plus 2 bar is 3 bar. Plus 3 bar, 4 bar. Plus 4 bar, 5 bar. And 1 plus 5 bar is 0 bar, right? I can think of this as a permutation representation as follows. What does 1 do? What permutation does 1 acting on the set do? Where does 1 take 0 bar? Well, it takes it to 1 bar, right? Where does 1 bar take 1 bar? It takes it to 2 bar, which takes it to 3 bar, 4 bar, 5 bar, and 5 bar goes back to 0 bar, right? Do I agree with that? So I might think of 1 as corresponding to this permutation, because that's what it does to the set, right? What is 2 bar do? Well, we'll see what 2 bar does. How does 2 bar act? Well, 2 bar takes 0 bar to 2 bar. 2 bar takes 1 bar to 3 bar. 2 bar takes 2 bar to 4 bar, 2 bar takes 3 bar, 5 bar, 4 bar, 0 bar, or it's 5 bar, 1 bar. And you might think, well, it's not very interesting, you just put things in different words. What's the permutation? Where does 2 take 0 bar? Now pick up where you left off. Where does it take 2 bar? Okay. And 4 bar goes to back to 0 bar, right? What's left out? Well, I don't know where 1 bar went yet. It goes to 3 bar. Goes to 5 bar, back to 1 bar. So notice that you might think of the element 2, it induces this permutation. Anybody want to guess what 3 bar does? Actually, maybe we can kind of do this just like we did the permutation. Where would 0 bar go when I act by 3 bar? Okay, pick up where he left off. Where does 3 bar go? Right. Y'all see the pattern here? This is how basically what we're doing is we're using this action to write Z6 as a permutation, a group, right? In fact, here's what it is. You can think of the following homomorphism. You can use this. We're used to writing this way, right? But you can think of this way. This is the identity. You can think of this as the permutation 0, 1, 2, 3, 4, 5. Now, what happens when you multiply this permutation by itself? Get 0, 2, 1, 3, 2, 5. Probably, no, don't. Okay, 3 times, didn't I? If you multiply this by itself twice, let's see, you go to 2, you go to 4, you go back to 0, 1, to 3, to 5, and back to 1. And 3 bar. What happens when you do this thrice? 1, 2, 3. 1, 2, 1, 2, 3, and 1, 2, 3. And these probably all look familiar. So really what you're doing is you're just taking the 6 cycle in S6 and you're looking at the powers of it that generates a isomorphic subgroup Z6 that sits inside of S6. So this is how, for example, when we took this action of the group on itself, just by adding things to the left side, we get a permutation. Does everybody see how we did that computation? Okay, good. So I'm going to throw a theorem here out at you. And this is going to be important for us in the sequel. Let G be a group, H a subgroup. Here we have theorem 518 something in it. Let G be a group, H a subgroup. H, G, a subgroup, and A is the set of left cosets. Of the left cosets of H and G. Again, G doesn't have to be normal. This is just a set of cosets. Suppose a G acts on A by left multiplication. Let G act on A by left multiplication. So let me show you what I mean by that. If I take an element of G and I act, so here's your element of G, here's your left coset. This is going to, since it acts, it should make a new left coset. Any guesses what would be a sagacious choice? What's the easiest thing so that my pea-sized little brain can remember? Well, how about G-X? Exactly. So G acts on this left coset just by multiplying. That's what I mean by left multiplication. There. Let pi h be the associated permutation representation of this action. Okay, just let pi be the associated permutation representation of this action. What do I mean by this? I just take my left cosets, all these XH's, and what do? I act on it by G, and I check out its orbit, and I just write down what the permutation is, just like I did here, right? So I start with XH, I act by everything on G. It makes a little kind of cycle, or maybe a product of cycles, and I get this associated permutation representation in the following whole. Number one, G acts transitively on A. Two, the stabilizer of H stabilizer NG of H and A. Remember H, this is just the special coset that is just, remember what we're looking at is the left cosets of H and G. This is just the identity H. It's that coset is precisely H. And here is kind of the big one here. The kernel of the action is the intersection over all G and G of G, H, G inverse. And this is the largest normal subgroup, G contained in H. This is the largest normal subgroup of G. Contained in H. Okay, any questions on that before we start digging into what's true? I think the proof, this is a good proof to do because it also, I think, will help familiarize ourselves with all these definitions in the language as well. Okay, questions? Okay. Let's prove one. Proof. So my first claim is that he acts transitively on A. An equivalent way to do that is given any two elements, there's something in G that takes that. So let's let XH and YH be an A. Right? Notice that YX inverse operating on XH YH. So action transitive. Remember, what it means to be transitive is there's only one orbit, or given any two elements of the set you're acting on, you can find something in G that takes this to this, right? Well, given my XH, my YH, all I have to do is I just kind of finagle this a little bit such that this thing hitting this equals that, and there you go. So it's transitive. Everybody okay with that? Number two, the stabilizer in G of this coset is precisely H. Well, first, let's notice that if H is in H, then H acting on H, and I'll put EH there actually I'll put it here. For mathematic purposes. This is HH, which is H. So H is contained in the stabilizer. On the other hand, suppose X stabilizes H, then X acting on H, which is XH, is equal to H, which implies that X is in H. And so that does it. H is contained in the stabilizer of H, and anything that stabilizes H has to be contained in H. So they're the same. Everybody okay with that? Yes.
Why do we have to do two different cases?
Are you complaining about my lack of efficiency? I'm not claiming that I couldn't have done this a little bit more efficiently. But certainly if you want to show that this claim here is this set, the stabilizer is exactly the set. And a standard thing, if you wanted two sets are the same, is you show inclusion both directions, or inclusion of, if you want to show A and B as the same set, A is inside of B, B is inside of C. But I'm sure that I could have streamlined this. Yes.
Wanting to do it in one claim, wouldn't your second claim be sufficient because you're saying everything that stabilizes has to be an H?
Yeah, like I said, I'm pretty sure that I could have thought this out a little bit carefully. I just went through the careful containments in both directions. How about this last one? This mouthful here. The kernel of the action is this thing. Well, I'm going to do kind of a set equality as we go along. Just kind of throw in the sets. So what is the kernel of the action? For IH, the kernel of the action, which is, so now perhaps it's a little bit more clear why they called it a kernel, because we defined the kernel of the action earlier. I mean, even before we started formally talking about group actions. And then we had this thing that's a kernel of a homomorphism. Why are they calling this a kernel of an action? And the reason is if you have this permutation representation induced by this action, that is actually a homomorphism from G into permutations of the left cosets. And so the kernel of the action is actually the kernel of that homomorphism. Right? Is the set X. This is the set of X in G. Such that G what it means to be in the kernel of the action is, it leaves everything alone. So when it acts on any left coset, it doesn't do anything to it, right? One thing, of course, again, that I know for sure is that the identity is in the kernel of the action. So let me actually show that it's that crazy intersection that we had up here. I'm going through this. So, kernel of action is the set of, kind of repeat what I got here, G and G, such that G acting on XH is XH for all X in G. So let me massage this. This is precisely the set of G and G, such that GXH equals XH for all X in G. Right. And so this means that, well, what does it mean for these two cosets to be the same, right? This means that this is the set of G and G such that X inverse GXH equals H for all X and G. And this is the set. Well, what does it mean for these two cosets to be the same? It means that this thing always has to be contained in H. This is the set of G and G such that X inverse GX is in H for all X and G. Right. And so I guess a good way to put this, so this is equivalent to G and G such that G is in X H X inverse for all X and G. There we go. So I've got my hand on what G is now. And this is the same thing. So let's read what this says. It's everything in G that is in X H X inverse for every X in G. So this is the intersection of X H X inverse as X runs through all of G, which is precisely what we predicted here. So there is the kernel of the action. So the last thing that I have to do here to really finish this off is justify, there was something about, this is the largest normal subgroup that's of G that's contained in H. Well, let me first point out, let me make a couple of observations. So I'm going to leave part of this as an exercise. I think it might be a good thing to think about. See if you can prove that if H is any subgroup of G, then the intersection of all conjugates of that subgroup is always normal. This is always normal in G. Let me give you the lazy person version. This thing we proved is the kernel of the permutation representation homomorphism. The kernel of any homomorphism is a normal subgroup. So that's the normality. It's certainly contained in H because H is one of the things in this intersection. if you take, for example, X to be the identity, H is one of the things you're intersecting. So this is actually a subgroup of H. So it's contained in H, it's normal in G. By the way, see if you can prove just from first principles that any intersection like this is always normal in G. Let's see, I said, so it's contained in H, it's normal, got that. And I think I said it's the largest normal subgroup. Well, so suppose N is normal in G and N is contained in H. Right? Then for all X in G, X in X inverse is contained in XH X inverse. Right? And if N normal, then X in X inverse equals N. Therefore, N is contained in XH X inverse for all X G. And so N is contained in the intersection. So in other words, if it's a normal subgroup and it's contained in H, then it's contained in this thing here, which is the last claim. Okay. Questions on that? Okay. Theorem. I want to give you a couple of really groovy theorems here. Finish things out today. The first one, theorem. And I've promised you this before. You've heard this around the campfire because I've said this. This is also a theorem of Cayley, as opposed to the one where you have an element order of P for every P divided over the group. This one's kind of a big one here. Every group is isomorphic to a subgroup permutation group. If P is a group, then P so well isomorphic to a subgroup of SA for some S for some A subset A. So what Cayley's theorem says is if you have any group, I don't care what it is, then there exists out there a set A such that G can be realized as a subgroup of the permutations on A. So a permutation group. And if G is finite, the order of G is equal to N, then G is isomorphic. To a subgroup. So now let me tell you, this is not always efficient in the following sense. Let me give you an example. Okay, then I'll have you. It's R5. So there's one SRS is R1. You remember that one, right? Do you remember how, this theorem here, Cayley's theorem says that D5 can be realized as a subgroup of S10. All right, everybody agree with that? Because in this case, D5 has 10 elements, so it can be put in S10. But we've done much better than that, haven't we? Right? I mean, this one's a big group. It's got millions of elements in it. We actually fit this one inside of S5. So this may not be a best fit, right? So actually, we know that we can put D5 inside of S5. Remember, it was generated by 1, 2, 3, 4, 5, and 2, 5, 3, 4. Remember how we did that one? Right. So sometimes you can do better. I'll give you a rather extreme example. S6 is a subgroup of S6. I think we can all agree that S6 is a subgroup of S6. Just blindly using Cayley's theorem, it says that S6 is a subgroup of S720. Very inefficient, right? So in other words, the point is sometimes you can be more efficient than this, but the theorem itself is wonderful because it's not clear at all, just from first principles, that everything is a subgroup of a permutation group, but it is, right? By the way, just for fun, Z6 is a subgroup of S6. In fact, we did this example today, right? Remember how we did the bit with the permutations of Z6 acting on themselves, and we got these permutations that are all in S6. Can anybody think what's the best we could do? Can anybody do better than S6 for Z6? I can realize this is a subgroup of S5. Anybody know why? What do you need to have a Z6 inside you? You need an element of order 6. In S3, the biggest order of an element is 3. In S4, the biggest order of an element, I guess, is probably 4. But in S5, there are elements of order 6. 1, 2, 3 times 4, 5 is an element of order 6. And that's the best. Okay, so let's see why this is true. This is actually very short because we've already done the heavy lifting on this. Oh. Let H, the subgroup of T, be the identity subgroup. That is to say, H is equal to just 3. This gives a homomorphism into into SG. Here I'm thinking of the group G as just a set, right? The permutations of this with trivial. This gives a homomorphism for G into SG with trivial curl. And the finite case is immediate from that. So this is, we've actually already done the heavy lifting, as I said in the previous result. We're going to prove the following result next time. Let me just throw this out. Corollary Let's suppose that G is a finite group of order n. And the order of G equals n. If P is the smallest prime such that P divides n. So take the smallest prime that divides n, and H is a subgroup of G such that the index of H and G is P. So H is a subgroup of the smallest prime index. I don't claim that H exists in general, but if it does, then H is normal in G. What is the smallest prime of them all? Somebody answer me that. 2. A corollary to the corollary is if you have a subgroup of index 2, it's normal. Because 2 is, if 2 divides, if there's a subgroup of index 2, then 2 is the smallest prime, so this automatically holds. So we'll see why this is true next time. Any questions? Any questions? If not, I will see you folks Friday. The math club today might be interesting, so stop by if you have a chance. Other than that, have a good week.